like coffee, like something like tea. It's more stronger tea.
Which type? Which type?
Usually drink espresso.
Okay, that's strong. Okay.
I had when I was finishing, I finished my master's at SIU and I was working as an adjunct. And I was going all over, like from Edwardsville to Belleville to Lewis and Clark College up in Godfrey. And so sometimes I'd stop at this coffee shop and drink coffee and grade. And I got to know the lady who ran it. Her husband was retired military. And when she found out I was once in the military, she would, you know, if I was in there, she'd say, hey, I got something new. You want to try it?
Right.
So she had me try this one drink and it was really good. It was strong. And it turned out, she said, oh yeah, that I gave you the orange drink. That's 7 shots of espresso.
No wonder it was.
So I didn't actually have to write on the board that night when I taught. I just put my hand up there and my arm shook and did everything. That was, I never drank a mystery drink from her again.
That's crazy, yeah. So Saudi Arabia, it's tea more earlier?
No, actually, yeah, it's given in people choice, but for me, I prefer Arabic coffee.
Arabic coffee, yeah.
Yeah, I know it's.
So talking about Arabic coffee and all that, I've always wanted this. I've been trying. Oh, I'm not wearing mask. I realized, sorry. Okay, it was not intentional. Must have a spare mask in the pocket. Okay. Yeah, so I was saying, we were talking about Arabic coffee. So I think I've been trying for the last 4 semesters, I think, to get together students. I think that's when I realized mask. I thought I was talking about mask. So now that the rules are at least lenient to a certain extent, seems to be safer. Maybe even if there is some problem, it might be down the week, 4 weeks or something, or maybe 3 weeks. So should we take this opportunity to get together on a Saturday, all students, not just this class? This is nothing to do with the class. Okay, so just a department something, and you think it will help?
Next Saturday.
I haven't decided anything, so you guys tell me. Is Saturday a good time?
Not for me.
Not a good time because kids are there. You can bring up kids.
No, it's gonna be so much.
Okay, so what time suits them? during class time. But that's not appropriate, but okay, so that's the challenge. How about this? You guys think about it, and maybe we should do this again. I should tell that I have tried this many times and it fails for some reason or the other, because I don't want to do it even if there's a small disagreement between, even if it is 1 in 5 or like it is 1 in 10 probably. Or if it is a nice disagreement, then that's okay. If someone is concerned, then I would just back off. It's not really. So that's what happened earlier, but this time it seems like maybe it is possible. I was telling that maybe on one of the Saturdays we should like Giant City is a good place. It's just you can have a small picnic kind of thing. I cannot. I don't think my family can cook so much, so I don't think I can afford to bring you guys. But yeah, if all of us go and have a lunch there together, everyone gets their own lunch or something like that. Simple, which doesn't take too much organization. I'm sure we're not do that. So I'll try something in the next 2 weeks or so, or 3 weeks, maybe end of March, maybe. It's right there next to the exam, so maybe this will be part of the exam, 20%. We'll see. Now that we have a challenge, like how to make it without Saturday. So, homework 5 and homework 6 has been delayed, but you guys decide on which date you want to submit, but do have a deadline among you guys and submit it. So I don't want to put a deadline, right? So there was a request for postponement. I think all of this. So it course keeps going, homework 7. So, but don't pile up. You don't want the deadline like 3 weeks down the line. There are 4 homeworks that has not been due. So that's not a, so take your time, but I'll catch up.
Did you post this one?
Yes, it is posted only about maybe 1 hour before the class. So maybe if you search it, even in the morning, you might not. Yeah, I did post it. So this is the 9th week. So we have about 5 weeks of classes remaining. There are 16 weeks in a semester, including the including the exam. So if it's a 9 weeks, I think we have 5 weeks of classes more. So might be just sufficient to what I have planned, unless we delay here. Usually you do get to certain things gets overlap.
It's an interesting way because we have by the ICCB, we have to have 16 weeks
Of classes.
of classes, and then we have a week of exams.
I noticed that, and it is so strict that even if you have a snow day and all, you have to at least officially get the class covered somewhere or the other. Probably it's the same thing here also. It's not 16 weeks of classes, including the exam week. But if you miss a snow day or something, I'm sure there is some rule saying that we have to cover it. But it is so, at least in these kind of classes, it's easier to, it overflows. There are concepts or topics that is so fluid. It's okay. But in the service course, that does become a challenge. In fact, not to say anything, just to cover the syllabus itself is a big challenge, at least for me. It's just too much, it seems like. And yeah, that's always a challenge, and I struggle at least. Yeah. Okay, so we did stationary action principle. We pretty much derived it. So we use the idea of functional derivative, write down an action. What we say is that any system is described by an action. And you say that the nature seems to have a special preference for this so-called action, and it tries to minimize. Right? So the most of what we see around us can be explained by saying that, oh, the nature is trying to minimize this action. And there we made this special consideration that, oh, we don't want to make these variations at the boundary. So it seems like nature is very picky that, okay, if something is happening from T1 to T2, it doesn't change that. And that's usually not the case whenever something is dealing dealt with in nature. It picks its own, like for example, coordinate system, who says XYZ is any special. Nature doesn't know which coordinate system they're working on. And these become statements like, for example, principle of relativity, which is called special relativity, that just says that any inertial frame, by inertial frame there, it means any frame that's moving with constant velocity. That is no specific pattern, it should be independent of that. That looks like a very simple statement, but when you say that that's a requirement, then there are consequences of it. So that's principle of relativity. So then you ask, is there any other such consequence, like if you rotate your frame, right, if the physics doesn't change, what are the consequences? And the idea is that these all lead to conservation principles. So stationary action principle, and how does this all gets related? And the point is that at the boundary T1 and T2, we want to make variations, and apparently, or we will show that this can be captured from that. So let's go back to our Lagrangian or the action, and this time put in the boundaries, right, and not have the restriction that that the variation of the boundary is 0. So let's state the problem more specifically. So we have an action. So what should I call this? I think it's stationary action principle in complete form. We earlier call it Hamilton stationary action principle. So it's stationary action principle. We talk about an action. It's a functional of the path the particle takes. It might be good to do one-dimensional, but I think we have had enough practice with variations, so hopefully I can do it in 3 dimensions. It doesn't matter at all. It's if I do it in 1 dimension at the very last step, I say that, oh, think of this as a vector, and that's all. You don't really need to do this. The content is there. If you have any problem with this vector sign, just pretend that this is 1 dimension, or ignore the vector. There's not much richness in the vector at this point in this discussion. So let's say now we didn't cap, so let me put some space here. I want to put 2 more variables there. We have been dealing with this, right? So T1 to T2 and Dt, and the Lagrangian is all as a function of time. T derivative of the position, the function of time. And the time itself, in general, that could be time dependence in the Lagrangian. Notice that the left-hand side does not depend on t, right? This is an integral variable. Like that's a dummy variable, so usually you don't depend on t. But what it does depend on is T1 and T2. Right? Those are special variables, and this is T1, comma T2. It doesn't depend on the integral variable time set, but it does depend on the time in the sense that it's the T1 and T2. So your action in principle depends on 3 variables, T1, T2, and R. R is a function of time. So in that sense, it's a function. And you might want to think of T1 as just a point in time. Right? That's the way you would think, but we don't want to have that liberty. We're going to say that T1 itself is a function. So that leads to the idea of time. How do we define time in general? If I were to ask, like, do we ever define time? And you will notice that, yeah, most of the times we have some properties of time. We don't really strictly say it. Like it's the first variable we talk about, right? That if you think of physics, the very first variable says that, okay, so there is an evolution. There is something is evolving in the variable of t. So we have the choice of, okay, you can take anything as t. But from that point on, and there is one restriction on t, that it has to be monotonic. That means time always increases. You don't go back in that way. A sine function cannot be a time. The sine function goes up and then comes down, up and down. Unless you think of our universe really oscillates. As of now, we don't know. Even if it is oscillating, does the time oscillate? We don't know. Right? But it does seem like from our principles that we are seeing, it seems like time has to be monotonic. It keeps increasing. We don't go back in time. So that's one property you need to have. But then what function should t be? Can be anything for that. Then you ask, okay, is there a choice? Should it be a single? What if I have a monotonic function from the usual time we say to another t? So what if I make a transformation in time? Does it matter? Like what in this world, if I change time for everyone, all the clocks are reset by certain amount and not even a linear amount, let's say by a functional amount, will we know about it? Like, is the question clear? So we have all of us have a time in the sense that we have a clock. And then I said that we overnight, by overnight, I mean that we don't know about it. I don't tell you when we are doing it, but I do it that all the times are changed in a certain manner. A functional dependence is there and I change it appropriately. Then will we know? But when we know, I mean that will our equations change? Like what we know is that our equations, that's what we depend on, our sensors depend on some equations, our nature is governed by some equations, presumably. We are able to understand nature. And the question is, can we know that? And if we can, if the system does depend on it, how does it depend on it? If it does not depend on it, what are the conditions? So that's the question. In that sense, we are saying that this t or this t1 and t2 is a functional. It can depend on something else, exactly like R. So then you ask, okay, what does it depend on? And it depends on t. So this R1 and R2 are really functional. So R, T1 and T2 are functions of time. Including T1 and T2, that's fine. Okay.
Is that a difference on velocity action?
No, right? That's our Lagrangian formalism does not depend on velocity, right? That's this. I change by R and the velocity changes in this manner. This is velocity. Right. Hamiltonian is slightly different. You say that the construction is in such a way that there is two independent variables. R and P are independently variable. Right? Here it's just R. You only change R. And because you have changed R, if 2 points are changed, then its derivative changes automatically. Right? In that sense, I have changed this, but that's a secondary variation. It's not an independent variation. Right? R is independent, velocity is a dependent variation. Like R decides what the velocity is going to be. Is that?
When I use T1 and T2.
What I mean by that is, what do I mean by T1 and T2? Is that the,
No, why we use T1 and T2? Because before we use only R and T.
we didn't use even T. There was no dependence here earlier. Right? Earlier, what we said is the following. So earlier we said this was time T, right? And this is your R, let's say, or let me call it one variable, right? And there was this some arbitrary path you could have gone from T1 to T2. And then you say that, okay, what if I change this function? So I said, I'm going to keep this fixed. Right? That's a new path. And you said that out of all possible paths, which is the path that keeps this minimum? And that path has a special meaning in the sense if the particle goes from here to there, it will take that particular. Out of all these paths possible, it will take the path that minimizes the action. But we said that whole argument depended on the fact that this keeps fixed. It's like a string, guitar string, right? Both the ends are fixed. And then you say that, oh, that seems to be a restriction, but what if I don't fix it? That's what we are investigating. So here what we're saying is that you're going to change this. This is allowed. You can vary this also. And then you say, okay, what does that mean, right? What do you mean by changing T1 and T2 itself? And especially as a functional, not like, see, T1 and T2, if you change, that's just changing the time points. Instead of the system going from T1 to T2, I'm saying T1 plus T2. That's not what I'm saying. What I'm saying is that I'm changing my definition of time itself. That's a functional now. So what I'm trying to say is that the usual T that we have, right? I'm going to redefine this as some T prime of T. That's a possibility, correct? Think of like, for example, this is very usually done in astronomy. In astronomy, there is a very nice parameter for time. Something is going around in circles, right? And the angle is always increasing. Like if you work in radians, 360, keep going. Don't stop at 360 and start going in circle. 0, 2 pi, 4 pi, 6 pi. So angle is a good measure of time. So in astronomy, you don't work with time, you work with angle. And then you have a relation between angle and time, which is phi is equal to omega times t, which is a simple linear relation. So you, or since angular momentum is mostly conserved there, there's an advantage in working with that. So my point is that you can work with any time. Who says that, or to begin with, how do we even select time? And then you, when you think about it, the first parameter, we didn't know. I mean, I'm sure it must have been very hard for the first person to have crossed that stage. Like, oh, which is the variable I'm working with? So in the times of Newton, probably must have, probably, I don't know. Okay, does that help in answering your question of what is T1 and T2 and what's the T I'm talking about a little bit?
But before we didn't have T1 and T2.
We had T1 and T2, but we didn't vary it. Now I'm going to vary them.
But the variation is in for our position, not in time.
Oh, okay. So what is going to happen is that even though I'm showing this pictorially like this, so actually what is happening is that this is the transformation I'm making. If I make this, this changes. But I'm allowing that also. So maybe I should say it is somewhere here and it changes here. Right? So T1 itself changes. Yes, that's correct. So it's on the x-axis itself. It's a functional. So it's very hard to show that on a line. Right? When the moment I've drawn a line, it's not a functional in a sense. Right? So I'm changing the functional itself. And when you do that, there is a part that contributes everywhere in the bulk if you want. And there is a part that contributes only at the boundary. And we'll get these two parts. One will be everywhere for the time, like our equations of motion, and one will be only on the boundary. And we will notice that the boundary has that interesting features. So, good point.
Here we just make it a small change from the initial and final position.
Yeah, as far as mathematically goes, we are just going to change T1 and T2. So the simple idea is that earlier we had one function, mathematically speaking. Now there are three functions. And it will be just a tedious calculation, just pretend that this is a mathematical variable. But at the end, we have to address the question, okay, what are we doing here? And when you think about it, then you realize that, oh, you're actually redefining time itself. So it's slightly deeper than what we have already been doing. But mathematically speaking, these are just three functions. And just pretend that we are doing functional differentiation. That's all we will be doing. Okay. So, or go back and think about what is the relevance of this, but mathematically speaking, just three functions, okay, if that helps. Okay, reasonable? Any other questions? Because that's a important that the motivation is clear what we are doing. Okay. Okay. So that, so let me. Okay, so you want to change this. So the change in the action to W now is R1, sorry, R plus delta R and that could be T1 plus delta T1, and that is T2 plus delta T2. That's the change, and you subtract the original value of the function. So instead of writing this whole thing, I'll get lazy and I'll say it's W plus delta B, right? So by this, what I mean is W, original W, I'm not going to write the dependence, plus delta W is basically this. I want to actually evaluate this down. But instead of writing that whole thing, I'm just writing it. Is that clear? Okay. So that's equal to, then I want to make a change everywhere now. This is T1 plus delta T1. This is T2 plus delta T2. And T inside is innocent, right? That doesn't matter. And L of R, there's T dependence in there, plus delta R. Like wherever it's obvious, I'm not writing the T dependence. There is a T dependence in here. There should be a T dependence in here. And now there is so maybe I should write, yes. Is that clear? Or maybe I should also point out that these two dependency, and here I think I've said this before once, this is implicit. Now that's explicit. And that plays an important role here in the sense that by implicit and explicit, what I mean is that when you do this integral, if I were to make this, I take some change in T, it is the explicit variables that change. T also changes, but that's a dynamical change. That's implicitly, it changes on its own. So that should be the difference between the time dependency here. In a sense, we are solving for R, right? R is our unknown. So T comes with it. T comes with the unknown in there. So one should differentiate between those two dependents. So whenever we do anything with this T where it is going, it should be clear that it is only on this T and T. Okay. So that's our definition. And of course, we are saying, how do we minimize it? We want to completely minimize that. But to begin with, what is this change? We want to calculate delta W. That's a simple goal we have as of now this whole lecture. We will just do what is the variation in W due to this case. Any questions at this stage? So if you allow me, let me operate this dr by dt. These are two functions of time. So let me treat them as two different quantities instead of rewriting. Let's save some plus d by dt of delta right, that's 2. That seems like a little work, like whenever you have some dependence in the limits, we don't usually work with it, but it should not be too bad. So how do we work with quantities in the limits? The basic idea is that bring it down, right? Make a substitution that moves this from the limits into the function. That's a simple trick you want to use. So how do we do that? And that's where this comes in. Right? We have this functional dependence. So we want to make this as a substitution now. It is this, the way I stated it, it seems like really it is T is linear and there is nothing happening. But this is the point where it becomes a change in time. So I'm going to substitute T prime is equal to T. I'm making an infinitesimal transformation. It's not any general transformation in time. It's an infinitesimal general transformation in time. So I'm redefining time. So it is T and I want to choose this properly. So this is t minus a small f. So this is a function of any function I want to add to t, the existing t. I want to add any arbitrary function delta t, a small tiny variation thing. So this was your question, that this is linear function of t here. So this is the transformation from the t. I'm going to another arbitrary form. This could be an arbitrary transformation in time. So this is delta t. So in that sense, you're saying that t itself is a function of time here, right? So that's a functional form here, and you make a variation in this. So let's say earlier it was line, and then you make a variation in that infinitesimal variation, which means to say that it's a general, any functional variation in it. So that's what this means. But having said that, I'll make one condition, that condition in the sense this is a substitution, right? I can do anything. This is just a mathematical manipulation I'm making. I'm not constraining the system itself in a sense, but what I will require is that this variation at T1, I made a change here. So this is T1. The variation at T1, I will say, is this variation that I am making. I made a variation there. I want that substitution in such a way that this is delta T1. Because we did make a variation delta T1, which was arbitrary to begin with. And so I require the substitution that I'm making to have this condition. Is that clear what I mean? And similarly, delta T, T2 should be delta T2. This is not really a choice. It's a choice in the substitution, but there is no generality being lost in doing this, because these were arbitrary to begin with. It's just that whatever variation you make, you have that substitution, have that variation. So if you think about it carefully, it is not a restriction on you're not lost any generality in the problem. The variation is still very general. Okay. And the advantage of that is, of course, that at the upper limit, so what happens at t is equal to t1 plus delta of t1. So at t is equal to t1 plus delta t1, because whenever I do this integral, I have to say what happens at the limits. So I'm going to change all the t to t prime. So when I substitute t equal to t1 plus delta t1, t1 prime, or t prime, sorry, t prime is equal to t1 plus delta t1 minus of this evaluated at t1, which is delta t1 itself, which makes this t1. So that was the purpose of the whole thing, that I remove all my variation out of the limits. And at t is equal to t2 plus delta t2, t prime is equal to t2 plus delta t2 minus delta t2, that's equal to t2. Okay. What I'm doing is that I'm making this as my substitution, and I want to rewrite this whole integral in terms of t prime instead of t. That's my goal. Okay. So I first work on my limits and say that, okay, if I substitute this, my limits are t1 and t2, that's gone. And now I have to work on dt. Like what happens to dt if t prime is equal to t minus this transformation? What is dt? So let's go and work on that. So t prime is equal to t minus delta t as a function of t, any arbitrary function in there. I am interested in dt, right? If I'm interested in dt to be written as t prime, I should solve for t here. Right? That's hard. Like I want to invert this function. if I want to invert this function, it's a slightly tricky process because t is equal to t prime plus delta t. But it's a function of t, not t prime. When I invert it, I would like everything to be a function of t prime. That seems like not easy, but then the advantage of working in infinitesimal transformation is exactly this, that I now, this is a recursive thing, right? T prime depends on t, but t is already that. So I substitute this back in it. It's like a self-reference, right? So it is t prime plus delta t of t. And I can keep doing the substitution because t is the definition to begin with. But that's where the infinitesimal thing comes in. I can expand this. These are small variations. So this is equal to t prime plus delta t of t prime plus higher orders. So this is delta t as a function of t. And then there is d by dt prime of delta t as a function of t prime. But that's second order, delta t to this higher order. So higher orders. They're doing the leading order contribution. So I don't have to worry about that. So it's remarkably, the inverse function is exactly the same as the original function, just plus. That's the advantage of infinitesimal transformation, that it's okay, you can do it either way. Now I can do dt. So I'm interested in dt here, right? So that's dt is equal to dt prime plus normal differentiation d by dt prime of delta t. Now at this point, I did not write that functional dependence. It's understood that it's t prime dependence in there, which we will write it as dt prime 1 plus d by dt prime of delta t. Here it's understood again that it's t prime dependence. So that's takes care of this. We have taken care of the limits. We've taken care of the t. Everywhere else, it's just substitute t itself, except that there is a derivative d by dt going out. We said this is an explicit dependence. We should be able to replace derivative d by dt also in terms of d by dt prime. So let's work on that. So we would like to substitute d by dt to t prime, but that's just chain rule. So it's dt prime over dt times d by dt prime. What is dt prime over dt? Go back to this. All right, so that's equal to 1. This is 1 minus d by dt of delta t times d by dt prime. So I used this relation in use. Like first I wrote this and then used this. Any questions? Okay. With all this, now I start working on this. Like I can now substitute all this just in principle, mathematical manipulations. Must be careful. So now the change in action is equal to now t1 to t2. Instead of dt, it is dt prime of 1 plus d by dt prime of delta t. And the Lagrangian has to be expanded. So it's r plus delta r. dr by dt, that is now t d by dt is this. So it is 1 minus d by dt prime of delta t, but oh, did I mess up? Oh, what was I doing? Yeah, so it seems like this is not complete, right? Because this is t prime. I want everything in terms of t prime. So it seems like this is d by dt. But again, invert this. Where is the statement of d by dt here, right? Put this again in a cycle. So this is equal to 1 minus d by dt again is dt prime over dt times d by dt prime of delta t times d by dt prime. And dt prime over dt again, we will use 1 minus this, right? And that will be second order. So if I replace this to just one order, this is equal to 1 minus, let me write this in two steps. So dt prime over dt is 1 minus d by dt of delta t d by dt prime over delta t d by dt prime. We want only the leading order, so that's equal to 1 minus just one has to be very careful. Either way, this becomes t prime. That's what here it was t. Now we get this as t prime. To the leading order, what it means is that to the leading order, d by dt is equal to d by dt prime. That's part of the inverse. So, like it's like this statement. So t minus d prime to d prime plus d prime. That's related. All right. Okay, if that's the case, then I can have this to be dr by dt. And there is one more term here. So this is cos t by or t prime d by dt prime of, let me do this properly. So this is d by dt prime, and then I write this as r plus delta. I think that's better. That way I don't have to show the t prime difference. It was d by dt that got replaced with d by dt prime. This plus this, correct? This is getting replaced with this. So, and eventually there is time, which is t prime plus delta t.
That one.
Sorry?
No, d to dt equals d to d prime.
This one?
Oh, yeah, upper.
Upper.
Yeah. It's that one.
That's because it's wrong, right? It is this one, yeah. Give me a second. Yeah, it is this statement here, okay. D by dt actually is equal to d by dt prime plus, right, this factor d by minus of d by dt of delta t of d by dt prime. But now you want to write the opposite. So you would say this is d by dt prime. Instead of going through all this, you can just say from here, put it opposite. That's d by dt plus, now it seems like, oh, this should be d by dt, delta t, and d by dt now. But only thing, now here I will make this a delta prime. So what I'm trying to say is that if I get this, the other one with, even if you blindly do it, even if you make mistakes, you're still getting it correct because to the leading order, it's always correct. So it's very possible that when you're first time analyzing this, let's say you're the first person to do this, and you made an error. Oh, you didn't take care of this t properly. You'll still get the correct answer, even though conceptually you made a mistake, because of the infinitesimal transformation. In infinitesimal transformation, leading order captures things even to the inverse functions. That's okay. And I think I said it wrong earlier that I said this is equal to this. That's what's your confusion. So this is the point I was making, is that if you know this, then you know the inverse function properly. In other words. Any other questions or comments? It's the same process what we were doing of functional differentiation, or it's basically variation, but now at the limits, and it is slightly tricky. Okay, but now from this point on, it's algebra. We just have to expand this out, throw away all the second order terms, keep the leading order terms, and not only leading order terms, the first term always cancels out with this W. Cancel this W, and whatever remains, keep the leading order. That's fine. That's our goal. Okay. First, expand Lagrangian. So this is L1 to T1 to T2, dt prime 1 plus d by dt prime L to T. Actually, let me write this once more. It's probably helpful to write this once more. So this is delta plus delta R. This one, there are 4 terms in here, right? So let me write this 4 terms in there. So that's 1 minus d by dt prime delta t. And then there is dr by dt prime plus d by dt prime times delta r, right? There are 4 terms. Multiply this out. This is the velocity itself. The first term. Second term is plus the variation, the derivative of the variation in velocity, or variation in position. And this is now the variation in the velocity due to the time transformation. And there are higher orders, delta square. Like the last term is 2 variations. There's a variation in time, variation in position. I am dropping all the second order terms. As far as I'm consistent, that's okay. I can still learn from all this. So my velocity gets 2 variations. Earlier there was only this. My velocity now gets a variation because I'm changing velocity or position, sorry. And I also get a change because I changed my time itself. So put that back in the Lagrangian. So that's equal to the velocity. So probably now I can start writing velocity names. So this is velocity, right? But not everywhere. This one I have to write this as d by dt prime of change in position, and minus of this is d by dt prime of delta t, like the transformation in time. What's the derivative? And this is velocity. Yeah, this is velocity. It's t prime dependence in all this. That's understood here, right? This is all t prime dependence. Okay, and there is t prime plus delta t. This is a function. So take a derivative, I mean, the Taylor expands. So Taylor expands, so this is T1, T2, T prime, 1 plus. Taylor expand, and I say L. The first term is just R V T. That's the first term. Second term is the contribution due to the change in the first variable. So that's delta R dotted with the change in position, which is basically gradient. Right? This is gradient of L. You get this earlier also when you did the usual without the time. This is the one that so right. Now there is a change. The change in velocity comes in two places. So this is plus d by dt prime delta R minus, this whole thing is a variation. Velocity, so let me put it like this, dotted with variation of velocity Lagrangian of this. And plus delta t partial derivative of L. Convenient on the screen, but advantages of the whiteboard. That's very clear. Like it's just Taylor expansion, leading term, first derivative, but the first derivative is one with this, one with this, one with this, three first derivative. But the derivative with velocity has two terms contributing. Now we just collect things together. That's going to be the idea. And of course, we want to have all this independent. This is acting on that we will integrate by parts, but we will come to that later. First, let's collect this. Any second order term cancel away, right? For example, when this multiplies with this, delta t and delta r, I drop. In principle, there is 1, 2, 3, 4, 5 terms. 5 into 2, 10 terms in principle, but many are second order. Whenever this multiplies, that's leading order, so that's 5. But whenever this multiplies, only this is leading, rest everything is. So there's 6 terms in leading. Subtract the first one because that's W. So overall, that will be about 5 terms we get. Okay. So let's collect all these things together. Back. Oops. Okay. So this is equal to. Is it clear when I say that W cancels this multiplied by this? When L multiplies by 1, that's W. Okay. And L multiplies with 1, that's W. So I'm going to cancel that right away. So I'm now writing only change and W. So that's equal to T1 to T2 dt prime. Write everything. So that's delta of R dotted with R, the first term, second term with velocity plus d by d prime of delta R. Dotted with L by dB. That's this term here. Taking care of this, taking care of this. Next one is minus d by dt prime delta t v dotted with dv. That's this term. Finally, one more t. These are the terms that I get when I multiply this with 1. But next I come with this one. I still get it d by dt and L. There's one more term here. Prime delta t and L. Rest everything is second order plus order squared. Okay, again it crossed, but I can for a while I can put that on the other side so that. Okay. Pretty much there. Now we just have to collect things together, right? See, delta R is here. Remember, if I want to do functional derivative, I want to collect all these things. In fact, you would have done a delta function, right? I would have done delta R here and got a delta function there and so on. But instead, I'm going to do integration by, in delta function, you do integration by parts. I want to do that explicit here so that I get it in this piece. That you get a derivative immediately. I don't want to write it as a functional derivative. I want to write it as a variational statement. Then I can read it out better. Okay. So I want coefficients of this separate, T separate, right? That's the basic idea. So wherever there is a derivative, we write them, undo the derivative by differentiation by parts, right? So basically the idea is wherever I get, for example, d by dt prime, here's t, right? And if there is a function f here, that's the same as d by dt prime delta t times f minus of d by delta t times d by dt prime. Is that clear? Okay, so I want to use this to replace, get that what I free the delta t that way, that's my point. I free it. And it doesn't seem like, oh, you capture delta t, you make it worse by putting it still here. But then this has a meaning in the sense that this is a total derivative. That's the boundary. Like total derivative is a boundary. Like total derivative of an integral dt going from t1 to t2, let's say g, right? What is that equal to? These cancel out, that's dg. T function. T1 to T2, and that's cool. That's only at the boundary. Right. And we want to try, and that's what the point is, that when you do this, things remain at the boundary, and when we want to interpret that in that form. Okay, that's just motivation probably for the next step. So let's do this back. So that's equal to, I'm going to collect things together, right? So this is T1 to T2 dt prime. This piece here, delta R, remains the same. Now, this one, as I said, there are two pieces to this. I write the second piece first. So that's delta R dotted with d by dt prime of dl by dv. But that's clearly not correct, right? Because that's not the same. These two are not the same expression. So I want to correct that by saying that, oh, that's the same as whatever is remaining. I write that as d by dt prime of delta R dotted with dl by dv. I wrote it below so that I collect all the boundary terms here, like in the next one. I've done this now. I've taken care of this. Do the same thing here. This is plus delta t and d by dt of v d by dt prime of v with L v. So that's not the whole story. So I just said total derivative there. So it's minus of this side. Remove the bracket here, put it back in. So this is T V. Yeah. That's this one. Take this down as two pieces, one here, one there. This one is straightforward. Put that as it is, plus delta t, delta L, delta t. No work needed. Cross the screen. And the final term here is minus of delta t times dl by dt prime. And again, open the bracket, put this back in, plus. Just nine equations in a sense, but are necessary to erase the board here. So I want to rewrite this now, just one small change that I'll collect this together. Delta t is a different kind, and these are all on the boundary. So three kind of terms. So the change in action due to the variation in R T1 and T2 is equal to the three pieces, T1 to T2, dt prime. Let me keep dt prime. At this point, I can change t prime to t, and that's okay. And I write delta. I want to collect all the terms that are delta r. There are only two terms, these two. dl and this is the only term you would have got if you had not changed the boundary. And if you remember, what is this equal to? This is your equation of motion, right? In the standard stationary action principle, you would have set this to 0, and oh great, this is your minimization principle, you should have got that. But now we have two more terms, so let's put that together. So the second term is, I'll write that as an integral again. This is the variation due to the time transformation that we made, delta t, and that can be written as, let me write that as, write dl by dt prime. This term first, d prime. I write this time the term first. Stop. Yeah, here this is not partial, right? So when I redid this, this was a total derivative. Right? Otherwise, this will cancel out. So when I did the partial to this, I moved this, and this one should be total derivative. And it is become. And if you do this, so this is partial derivative, I put it here, and plus we dotted with minus L. Oh, divided by dt prime of does the quantity in the curly bracket ring a bell? Is this familiar? What is that? That's a Hamiltonian that's showing up. And it is the time period. So that's naturally in there. So we will see the meaning of all these things. First. Now this is the boundary term. Boundary term has total derivative d by dt prime. So this contributes only at the boundary, and that's delta R with L by dV minus of delta T. Again, let's write this as V dotted with again, you see the Hamiltonian showing up at the boundary also. And that's your, if you want the tedious variation of the action in complete form, but now we have to read out what is the minimization principle. And we have to talk about what exactly is the minimization principle. So let's do that. Any questions at this stage? Right, point to ask questions if you have questions on the algebra part. Okay. If there are questions, let's see. Now we say what is the action principle. So now notice what is the variation in the action. Now we can do functional differentiation, right? Delta R of T. What's that equal to? Then you would say, that is this piece down there. So that's the L by dr minus d by dt. Oh, and then one more step before I go in there. Sorry for the change of plans. Let's do some small definitions at this point. It helps to just for writing purposes. That the coefficient of delta R at the boundary, we'll call that the momentum. So this is a definition, right? These are definitions. Let's define canonical momentum as dL by dV, which is right here, right at the boundary term. That's all we are saying. So that's canonical momentum. And the coefficient of delta T will be defined as a Hamiltonian. But here, this is the contour. So now we are saying what is actually delta R of T. It gets a contribution from here, right? So that's this value. So this is d by dt, dl by dv. And what else? What else? You would say that, oh, there is a delta R here also, right? And then you would say, oh, how did I do my functional derivative? I did my delta divided by delta R, then there was a delta function. The T, if the time I'm talking about is at the boundary, then this contributes. Right? Only if it's at the boundary, because this is just for, so this is equal to, say, if I'm dividing this out, this is very clear. Let's do this in 2 steps. Okay, change your mind. Maybe this will help. So do that here. So this is T1 to T2 dt prime, this piece here. This is a delta R T prime, and this is a delta R T. And dotted it. Partial derivative of R minus d by dt prime. Of actually P, right? The rate of change of momentum is the force. And there is another piece in here, plus E1 dt2 dt prime d by dt prime. And there's a contribution from here. So that's delta R prime over delta T dotted with P. And you would say this is a delta function immediately, so that you would say this is L by dr minus d by dt prime, d by dt of t. And this one now, this is a delta function, but since this is at the boundary, so this is equal to, since it's at the boundary, this gets evaluated at plus delta of t prime minus t this is dotted with this. It's slightly tricky thing. What should I say? T, yeah. T as a function of t prime evaluated at t prime is equal to t2 and t prime is equal to t1. The boundary, that's what, which is 0 if this is not the same t. If you're not talking about the time at the boundary, that's 0 immediately. So this is equal to t1. There's an integral of dt. So this is equal to L by dr t p plus p of t2 times t2 minus t minus of p of t1 1. So the main point is that this term does not contribute only unless you're at the boundary, unless you're talking about right at the boundary, doesn't. So we have now restate our stationary action principle. So overall, what this boils down to is that what is stationary action principle? Stationary action principle still remains the same, that we need the variation to be 0 at the boundary. These two have to go to 0. So you require that to be 0. And you read this out. This is your action principle. That's your action principle. These two go to 0. That's a dynamical statement action. But now you ask, what is this? Then you say that once the action principle has been used, then we are talking about motion. Once the action principle is minimized, that's what the evolution of a system is. And once these two are 0, the change in the action, this is your evolution. And we want to now see what does that mean. Like when we are saying that there is a change in R and change in T, that remember this was arbitrary, right? We are saying any variation in our coordinates, how does your evolution change? Evolution means how I'm evolving. Like I asked the question, if I were to change my time or position suddenly, will I know, will my evolution change? If suddenly when I'm sleeping, someone changed the clocks everywhere, all the clocks in our room, will I know about it? And that's that evolution. This will tell us. If this was 0, then that means that I won't know about it. If this is not 0, then I will know about it. So then we will conclude some things out of these quantities. Okay, that we will have to come back and do it. So let's keep this expression and let's come back to this. So the physics part of this expression, we will do it in the next lecture. Today it was the mechanical part where we derived all possible variations. Now you want to investigate what does this mean. And your homework is the third term. All your homework is doing is in this third term. Okay, we will make some change. Like I said, we will rotate our frame and then say, oh, does it change or not? And if it does not change, what do you learn out of it? And what do we learn is the conservation principles. So this is the connection between conservation principle and symmetry. That's the way you put it. The Noether's thing. So that's what your homework is all about. But let's. Okay, thank you.